In this video we are going to be talking about constructing a dual of a linear programming problem. The theory of duality is one of the most important concepts in linear programming, both from the theoretical and practical points of view. The basic idea is that every linear programming problem has an associated linear program called its dual, such that the optimal solution of the original linear program also provides the optimal solution of its dual. So let's start by first making some observation without going into any more detail. I have selected a 5-variable 3-constraint maximization problem. Constraints are in the form of less than or equal signs. Variables are greater than or equal to 0. Dual of this problem is in the form of a minimization, 5 constraints and 3 variables. If we look at the tabular solution through simplex method for this problem, we will notice that there are subtle similarities between some of the answers of both problems. And we will discuss this in a little bit more detail. Now, if we look at the standard form of both problems, let's assume u1, u2, and u3 are slack variables for the primal problem, and v1 through v5 are surplus variable for the other problem. Now, if we look at the optimal solution for both x's and y's and z and w, we will notice some very important characteristics in there. For example, if I multiply the optimal solution of xj's into the optimal values for the vj's, I would notice that they will be 0. Similarly for yi and ui. I also noticed that the value of the z and the value of the w at the optimal solutions are the same. So some of these observations are going to be helpful to us. Let's take another example. In this case, I have selected a 2-variable problem and 2 constraints because I can just simply graphically show what is going on. Its dual will also be a 2-variable problem that I can graph them and find the optimal solution. Notice the optimal solution, notice the feasible regions. Let's pick one feasible point in each one of those 2 problems. So arbitrarily we choose 2 feasible points. Remember, just 2 feasible points. From the first one, 3 and 1, and from the second one, 8 and 2. These are 2 feasible points associated with their values. Now, if I plug these values back into the objective function for each problem, for the first one, I will get the value of z17, and for the second one, I will get the value of 84 for w. So for maximization, I get 17, and for minimization, I get 84. Notice that the value of the maximization problem is smaller than the value of the minimization problem. And don't forget that this is for feasible points of both problems. In general, it's always true as you go through these different tableaus, the values of w gets smaller until it reaches the optimal solution, and the values of z gets larger until it reaches its optimal solution. Another observation that we can have in here is that if you write the dual of a problem and write the dual of that dual problem, you will notice that it would end up with the original problem. So one of the main theorems that we will have in this area is just this simple concept that dual of a dual is the primal, or the dual of a problem is the original problem. Let's look at some important theorems that are related to the relationships between these two problems. Mathematically, the symmetric primal-dual problem is represented as a maximization for the primal and a minimization for the dual. All primal constraints are in the form of less than or equal, and all dual constraints are going to be in the form of greater than or equal, with all variables to be non-negative. We just learned the theorem that the dual of a dual is a primal. Now we are going to introduce another theorem, weak duality theorem, and it simply states that if you have two feasible solutions for primal and dual, value of the objective function of the primal is going to be less than or equal the value of objective function of the dual. This was represented in the same observations that we did earlier. My preference for stating this is that we always say the objective value of the maximization problem is less than or equal the objective value of the minimization problem. Another theorem that we are going to be looking at is the strong duality theorem. It simply states that if primal has an optimal solution, then the dual will have an optimal solution and they are equal. That's the main condition. What we are saying is Z star is equal W star in both cases. This was also demonstrated in the simple example that we had with both Z and W to be equal 100. This is really the part of the weak duality theorem that has the equality sign in it. Another very important set of conditions in here is called complementary slackness conditions. Some people call it theorem, and it says that at the optimal solution, this relationship exists between the variables of one and the slack variables or surplus variables of the other problem. At the optimal solution, if you multiply xj star by vj star, you will get 0, or yi star times ui star, you will get 0. Again, this was demonstrated in the sample example that we did in here. X2 times v2 is actually going to be 0 times 10 equal to 0. Again, very significant conditions, and it has wide application in theory of duality. A lot of important conclusions can be made from this concept. Before actually showing you how to construct the dual, let's mention a couple of points that always causes problem for the students. One is that always try to write the coefficient of a variable in the same column. Second is always refer to a problem as a max or min problem and its dual. Do not assume that you always begin with a max problem to find its dual. Your original problem may as well be a minimization problem. To construct a dual, you can memorize a table similar to this one, or you can follow these simple steps. Learn to do a standard max problem, find its dual, how to find its dual, and then make adjustments accordingly. First, the max becomes the min, then you have new variables, z and x becomes w and y's, then b and c vectors will change their locations. B becomes c, c becomes b. For the main constraints, A matrix becomes A transpose. For example, for x1, if the coefficient of x1 is 1, 3, and 1, it becomes 1, 3, and 1 for a row in the first constraint of the dual. Similarly for the second one, and so on. Now, the problem with the signs that always people make mistake is that they are trying to memorize it the same way that it is represented. Instead of that, I'm suggesting that you look at it like this. Max problem to min, the signs, the first group of signs, less than, greater than, and the other one greater than and greater than. We are going to show you how to write a dual of a problem in a very simple format. And then we will make adjustments accordingly. This is the problem that we have in the video that you looked at them so far. And we want to write its dual format. Remember the steps that we talked about. First, it's a maximization, so you will have a minimization problem for your dual. Then you would have the variables z and x's in here. You will have the variables w and y's. We have 3 constraints and 5 variables. So in here we will have 5 constraints and 3 variables. So our variables will be y1, y2, and y3, and our constraints will be written down here. I'm going to just write all of those in here. Then we would have our variables, non-negativity or special conditions that we would have. y1, y2, and y3. Now that we have set up the general picture, we now need to look at the coefficients and right-hand side and the price or cost factors. First, we said that this B becomes C in here. So we will have 50, 30, and 20. And these are plus signs between them. That takes care of the objective function. Then the C values in here becomes the B values for the dual. So that is 2 minus 1, 2, 2 minus 1, 2, 3 and 4, 3 and 4. The next thing was to create the coefficients for these variables. Remember that it is a transpose matrix. This column, which is 1, 3, and 1, becomes the coefficients of this row. That's 1, 3, and 1. The coefficients of x2 in here becomes the coefficient of the second constraint there. So it's plus 4 minus 3 and plus 1. So it is 4 minus 3 and plus 1. X3 is 1, 0, and minus 1. So this becomes 1, 0, which erases this value, and 1. x4 is 2, 2, 0. So it will be 2, 2, and 0, which will erase this variable from here. Last one is 3 plus 1 and plus 2. So it will be 3 plus 1 plus 2. We have now created the main constraints of the dual. The last thing that we need to do, and those are the tricky parts that most people make mistake in them, is the signs in here. We need the signs for this. We need the signs for this. Remember the way that I talked about it in the video. Max, min, these less than or equal, these greater than or equal. These greater than or equal, these greater than or equal. It is that easy. However, remember that the signs actually are related like that. So these signs actually identify these signs. And these signs are opposite to these signs. But the trick that I talked about it in the video for you to memorize it is to just say max, min, less than, greater than, greater than, greater than. This would create a standard symmetric problem, writing the dual of this problem. Now, any other change in this system requires that you make adjustments to this. So instead of memorizing what happens if this is less than or equal or greater than or equal, just try to remember this format in your transferring from primal to the dual. If you do that, then the rest is as simple as this. Let's look at some cases. For example, what happens if this, instead of less than or equal, is greater than or equal? Remember the relationship. The sign of this constraint is related to the sign of this variable. Right now, you have less than or equal in here and greater than or equal in here. What happens when this is changed, that is going to also change. So instead of memorizing this, if we have a case in which this constraint is greater than or equal 50, the change in here will be the opposite, which is less than or equal 0. What happens if a variable in here, instead of being greater than or equal to 0, is less than or equal to 0? Let's say x4 is less than or equal to 0. The relationship again is with the constraints. x4 is related to the fourth constraint. Is related to the fourth constraint. Oh, I forgot to put these signs. It's related to the fourth constraint. That way, if this is changed, that fourth constraint will also change from greater than or equal to 3 to less than or equal to 3. That's simple. You can just change what you need to do. And also remember, if If you have a variable, for example, that is unrestricted, if x5 is unrestricted, x5 is associated with the fifth constraint. And because it is unrestricted, this sign changes to equality. So if you remember this format, you would never make mistakes. You always have this basic format in mind, and any change, you make it accordingly. What if we have one of these constraints in the form of equality? Let's say that this one was in the form of a equality sign. This is an equation by itself. So associated with this, remember, it's associated with the variables. Constraints are associated with the variables. So if this is equation, then third variable will be unrestricted. So in general, if you learn the basic format, you can write the dual. If it is maximization, it becomes minimization. How do I write the dual of a minimization problem? Let's look at this. It's a minimization. This becomes a maximization. Variables, they are y's in there. Doesn't make any difference. It's just a notation. A different notation. In here I will pick z, and my variables will be x's, for example, in here. I have 3 variables in here, so I will have 3 constraints in here. I have 5 constraints in here, so I would have 5 variables in here. So I'm going to write those variables: x1, x2, x3, x4, x5. And 3 constraints. The general picture for them will be I want to see what the relationship basically is for these variables and the constraints and the coefficients and the signs. So let's look at the coefficient matrix in here. For y1 I have 1, 4, 1, 2, and 3. This column becomes the coefficient of the first row. For y2, this column becomes the coefficient of this row. And for y3, this column becomes the coefficient of that. The 2 other things that we have talked about them is that this b vector in here becomes the c vector there. So 2 minus 1, 2, 3, 4. 2 minus 1, 2, 3, and 4. The coefficients of c in here becomes b for this problem. So 50, 30, and 20. 50, 30, and 20. And these coefficients: 1, 4, 1, 2, 3. 1, 4, 1, 2, and 3. 3 minus 3, 0. 3 minus 3, 0, which will erase this variable altogether. 3 minus 3, 0. 2 and 1. Plus 2 and plus 1. And for y3, 1, 1, 1, which is this one, plus x1, x2, and x3. And then I have 0 and 2, which will erase this together. plus 2. Now, this is the approach that I like to do for not making mistake instead of memorizing everything. At this point, instead of still going back from this problem to this problem, which requires me to just memorize some stuff, I would always remember first the relationships that we would have and the signs and the way that we have these signs. The relationship in this format, that the signs of the constraints are related to the signs of the variable in the other problem, and the signs of the constraint in this problem are related to the signs of the variables in this problem. So at this point, instead of going from this problem to this problem, I'll go back to what I have learned. I will look at this and I say, okay, this is supposed to be less than, max, min, less than, greater than. So these are going to all be less than or equal. Signs greater than, greater than. So these are all greater than or equal 0. They are all non-negative. Again, I should emphasize that the way that I'm asking you to just learn it is different than the reality. These signs are related to this, but they are opposite signs. That's causing sometimes confusion. These signs are the same as those signs. So instead of memorizing something like that, just memorize the general form and then accordingly change it. Again, if instead of, for example, this one greater than or equal, if you had less than or equal, if you have this relationship in mind, you know that that is related to the first variable in here. If that changes, this sign will also change to less than or equal to 0. If this variable, for example, let's say this was an equation, fifth constraint, and the fifth constraint is related to the fifth variable in here. If that is an equation, then this variable becomes an unrestricted. So it is that simple. Let's look at the variables, for example. If this variable y2 was unrestricted, for example, what would happen to the second constraint in here? It would change to an equation. If this variable was less than or equal, what would happen to this? Y1 is associated with the first constraint, and if that is less than or equal, this is going to change to greater than or equal. If you approach it like that, you will never make any mistake in this problem. The other thing is that always when you are dealing with a minimization problem, don't apply the maximization rules to it. They are different, and that will cause creating some general mistakes. So let's learn it like this, and you will never make any mistake. One additional thing that I would like to emphasize in here is the way that you are writing the problem. As I have mentioned early in this video, you have noticed that I'm emphasizing writing these variables underneath each other. do that. So if you are getting for example, a problem which is in this form, 2x1 plus 5x2 plus x3 less than or equal 10, and then you have 3x2 plus x3 greater than or equal 15. Don't leave them like that. Instead of writing this the same way that it is written in here, change the form. Change the form such that they will show up like a matrix notation. Instead of having 3x2 plus x3 greater than or equal to 15, write 3x2 plus x3 greater than or equal 15. That way, by just looking at it, you can realize that x1, for example, the coefficient of x1 are 2 and 0. The coefficient of x2 are 5 and 3. The coefficient of x3 are 1 and 1. And your right-hand side is 10 and 15. And that's what I have followed in here. You follow these simple rules, you won't have any problem in creating a dual of a problem.